We're going to continue with the periodic trends. And we talked about atomic radius. What happens to the radius of the atom as you go across a period? It decreases because of the increase in effective nuclear charge is correct. Good. We want to talk a little bit about ionic radii. This is going to be the radius of an ion. Cations, do they lose or gain electrons? They lose. So what's happening here, for example, if you have aluminum and you form an aluminum ion, you will lose the 3 electrons from the outermost shell. The nuclear charge hasn't changed. It needs to act on 3 less electrons. In addition, you're only going to have electrons into the second shell now. So a cation will always be smaller than its corresponding main group representative element. So cations have smaller radii than their corresponding element. An anion, on the other hand, is going to gain an electron or more electrons to the outermost shell. If you generate a fluoride ion, you'll gain an electron to the second shell with no change on the effective nuclear charge. So now you have the same positive charge acting on more electrons. So what is the anion's radius going to do compared to the atom? It's going to get larger. In addition, you'll have electron-electron repulsion, further causing that push out. So a cation will be smaller than its corresponding atom. An anion will be larger than its corresponding atom. And that is written out here. In regard to the cation, the electrons are lost from the valence shell, and the Z effective being unchanged is a little bit unclear. Let's say the nuclear charge is unchanged. In addition, in most cases, the valence electrons are closer to the nucleus with less electron shielding. And that, I think, might be a better explanation. The anion one is pretty obvious, and again, that explanation is written out for you. If you have a series of isoelectronic ions, they all have the same electron config. The greater the nuclear charge, the smaller the ion. So all of these ions are isoelectronic. And what you're going to find with main group elements forming ions is that the greater the positive charge, the smaller the ionic radius, the larger the negative charge, the larger the radius. I don't think you're going to see much of that, so I'm not going to worry about it here. The next trend we want to talk about is electron affinity. Electron affinity, as you said earlier, deals with attracting and holding an electron to the outermost shell. It's the energy associated with the atom's ability to attract and hold an electron that it didn't have previously. We have already established that across a period, the effective nuclear charge increases, resulting in a smaller radius, and you're going to see a larger electron affinity in most cases. There are some anomalies here that we're going to get into this year. There are some anomalies here that we will get into this year. What's an anomaly? An outlier, a discrepancy. So if you think back to biology, like trisomy 21 is a chromosome anomaly where you don't have 2 of every chromosome. In that case, you have 3 copies of chromosome 21. We're going to take a look now at electron affinity, some of it review from last year, but we're going to introduce the anomalies. Not difficult if you know how to write and draw electron configs, which you should know how to do. Electron affinity is the energy change that occurs when an electron is added to a gaseous atom. So you're looking at the atom's ability to attract and hold an electron it didn't have previously to its outermost shell. Fluorine can attract and hold an electron and form a fluoride ion. The electron affinity energy is negative 328 kilojoules per mole. Kilojoules is a unit of energy, 1 mole of fluorine. This is exothermic because it's negative. In general, electron affinity will increase that it becomes more negative or exothermic across a period. So if you look at the graph shown here, this is a little bit odd because you're seeing this as an increase. It's getting more negative, more exothermic. Here's the 0 line, so below that line you'll be endothermic. Generally speaking, if you look at group 2, from lithium to fluorine, you will see an increase in electron affinity across a period. No, I'm sorry. Yeah, an increase in electron affinity across a period because of the increase in the effective nuclear charge. But you see a few dips. In what group is beryllium? 2. In what group is nitrogen?
15.
In what group is magnesium? Phosphorus?
15.
Calcium?
2.
Arsenic?
15.
So there's something about groups 2 and 15 that sometimes put it into the endothermic range. And that's what we want to look at. We want to look at the anomalies. It's written out there for you, but I want to draw it so you truly understand what's going on, and I want to point out some mistakes that kids sometimes make. Careless mistakes. All right. We're going to take a look first at lithium. So we're going to look at group 1, lithium. Group 2, beryllium. Group 3, boron.
Can you move it down? Thank you.
Correct. I'm old and I'm showing my age. It used to be 3A. Group 13. That's kind of sloppy. Yeah, it just looks like a big mess. We can fix, no worries.
Wait, it used to be 3.
Well, yeah, the group numbers have changed, I'll show you, and I'm still stuck. Actually, you can see it right here, too. We learned it differently. I'll one day adapt. So see how it's 1A, 2A, 3A, 4A, 5A? And these are the B. So I learned the old method. That's all right. Just showing my age. In any event, in terms of electron config, we've got 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1. If I just draw the last subshell, I've got 2s, 2s, 2p. And here I would have 1, I have 2, and for 2p here, I have 1. So this is 2s, 2s.
Is that what you were saying about like the empty desks? Like you can't
Yeah, this is an unoccupied orbital. You don't throw it out. It's the same thing with the shell. Kids will say, oh, magnesium only has 3 shells. No, it doesn't. It has 7 shells, just like all the rest, but it only has electrons into the 3rd shell. So we don't throw the shells out either. Although I guess if you were eating nuts, you would, because that'd be disgusting. But we don't eat nuts in here because they're gross. Alrighty. Here we go. Electron affinity is the energy associated with the atom's ability to attract and hold an electron it didn't have previously. So, for lithium, you would want to attract and hold an electron, and this is kind of weird because you're going to make this, right? Which is not your common ion. Kind of looks funny. But that other electron would be placed here. All right, we have space for it, no problem. Well, if you want to attract and hold an electron for beryllium, you're looking at this. Where does the electron have to go? The next subshell. Not the next shell, the next subshell. You would have to introduce it into the 2px. That's another thing I want to mention. When you have a P subshell, it's typically PX, PY, and PZ. So for beryllium to attract and hold an electron, it would have to attract it to the 2px orbital of the 2p subshell, and you will see that electrons in the 2p subshell are not bound as tightly to the atom's nucleus as electrons in the 2s. Some of this will be much clearer next time when we do PES. When College Board initially said, oh, you have to cover PES, I looked at it, I'm like, what is this? I have never learned this in all my years of chemistry. And I spoke with some chemistry professors at FAU and up at Hopkins, and I said, do you teach this? They said, no, what is it? So I did a lot of research and taught it to myself, and after fighting initially with it, it actually makes a lot more sense to understand the trends, and we'll get into that piece on Monday. In any event, the reason why you get a slight dip in electron affinity for beryllium is because the electron would be attracted to the 2px orbital, which would not be bound as tightly to the nucleus of the atom as what you had previously, and therefore it's not favorable. In contrast, for group 13, you'd be attracting and holding an electron to the 2pz orbital, and you already have one in the 2px, so it's not that unfavorable. But in regard to group 2, you would be attracting and holding an electron to the 2px orbital, which would not be as bound as tightly to the nucleus. You'll see that it has lower binding energy than what the 2s orbital has, and we'll explore this concept of binding energy in more detail next time. The other anomaly that you see with electron affinity, you mentioned group 15. So let's take a look at that one. We want to look first at group 14 because I want you to make comparisons, 15 and 16. So you're looking at carbon, nitrogen, and oxygen. And carbon is 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4. Why are all of those paramagnetic? They all have unpaired electrons, and that's what I'm talking about. Things that have been mentioned previously, I realize mentioned today, but I'm just trying to make sure you're digesting.
For the first one, would lithium be more favorable than?
It's not a favorable issue. Generally speaking, electron affinity increases across a period because of the increase in effective nuclear charge. The ability to attract and hold an electron with a greater effective nuclear charge would increase. However, you don't see that in group 2 because even though it has a greater effective charge than lithium, you would be attracting the electron to the 2px orbital, and it has lower binding energy than the electrons in the 2s orbital. And we'll get to the binding energy concept in a little more detail on Monday. That's the beauty of PES, if there is a beauty to it. You also see an anomaly with group 15, which I'll hit in a sec.
Does that mean that a lithium ion would be isoelectronic with a boron?
A lithium ion, a beryllium ion, and a boron ion will all be isoelectronic with each other as well as helium. But be careful here because we're gaining electrons here, so don't confuse. These are not isoelectronic.
Oh, you can't have isoelectronic?
No, well, only if you form their typical ion. Lithium plus, beryllium 2 plus, boron 3 plus. Those are isoelectronic. These are gaining electrons they didn't have previously. Those are just losing their valence.
Okay.
All right. So what you've got here then, again, the 2px, the 2py, the 2pz, up, 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 down. Again, mastery of this concept before walking in the door. If you didn't have mastery of this, a little bit messy. In any event, we're looking at the ability of this atom to attract and hold an electron it didn't have previously. So we would be making C minus, N minus, O minus. Doesn't matter if it looks funny. If we were looking at C minus, that next electron would go right here. No biggie. You have space for it. It's all good. The higher the effective nuclear charge, the increase in the atom's ability to attract and hold an electron. For an N minus ion, you would need to attract it and hold it where?
The X.
Right here. Now, 2 electrons can fit in the same orbital and they'll spin in opposite directions, but they're both still negative. So what are they going to do? They're going to repel each other. So the reason why you see that dip in electron affinity for group 15 is you would be attracting and holding the electron, in nitrogen's case, to the 2px orbital that already has an electron. You're going to introduce electron repulsion, hence the decrease in electron affinity. You're going to see this in group 15. The kids are usually golden at this, but then they make the most careless mistake. Because I've talked about nitrogen here, they're like, oh, everything goes into the 2px orbital. Well, look at phosphorus. To which orbital would that additional electron go? 3px.
What?
Where would arsenic's additional electron go if it attracted and held? 4px. Where would antimony's go? 5px. Pay attention to the period. That will specify the orbital. Be very careful. I've asked about arsenic in the past, and kids are throwing the extra electron into 2px. They totally get it. They've written half a page, and then they write 2px orbital, and that's all it takes for a big X and big disappointment. Careful, careful, careful.
So for the group 15 elements, it's just that they're adding it. You're adding another electron in the px of whatever period they're in, causing electron repulsion.
And as a result, the electron affinity shows a dip rather than the increase, which you would predict from the effective nuclear charge.
2 is only because it moves up in orbital.
Because the electron would have lower binding energy in the px as opposed to s. That I'm going to explain in more detail on Monday, so hang on to that thought because it's so easy to understand with PES. In regard to your explanations, you will see that they are very well spelled out right here. So you've got them. Just apply them to the correct period. But the binding energy, this came up period 2 also, and they had a hard time letting go. What we're going to introduce on Monday is something called PES, and it's shown right here. These numbers show the binding energy, and you'll see electrons in the first shell are bound more tightly to the nucleus of the atom than electrons in the second shell. But you'll also see that in the second shell, electrons in an S versus P sublevel have different binding energies. These are not bound as tightly as these. But we will go into that on Monday, I promise. So accept it for now, please, please, and I promise as it all comes together on Monday, it'll make more sense.
How much of the packet can we do?
I'll explain that too.
So if you were to ask about the arsenic, you would say that the extra one goes into the 4 p atoms.
Correct. Correct. Just be careful. And that's the difference between understanding with sleep and being able to think and understanding with 2 hours of sleep and making a careless error. All right? Chemistry is so hard, and you've got to be able to think on every single quiz test, and in particular in May. If you can't think, you're going to make careless mistakes. You'll know it all. It's all stuffed in there. It's finding out which disc it's on. So you've got to be able to think.
What did you say was the mistake that
They put it in the wrong orbital because they're in the wrong period. So pay attention to the row in which your element is located, and then you'll be golden. All right, so those are the anomalies. Down a group, there are no anomalies. It's very, very straightforward. As you go down a group of the periodic table, down a group, the electron affinity decreases because you would be attracting and holding the electron farther from the nucleus, specify the shell, with more electron shielding. So that's just like you learned in honors. And we just want to make sure that you have a high comfort level in this type of explanation. The first one is tricky. That's an anomaly. They're not always going to expect you to recognize, ooh, group 15, nitrogen's electron affinity is going to be less than that of carbon. They're going to tell you. They're going to say, explain why. I can't tell you how many kids write on exams, you are wrong, it is this way because. No, no, no. Especially on the AP exam. I make mistakes, I'm human. The AP exam has been scrutinized by so many people, the chance of human mistake is essentially 0. If they tell you it's one way, explain it. Come up with something good. So take a minute now, write out answers for these 2 problems. We'll read them aloud, we'll strengthen them, we'll make them beautiful so that on your quiz you nail it cold. I'll briefly explain electronegativity and we'll wrap it up. I do have a POGIL packet for you that deals with the trends. Unfortunately, we're not going to hit ionization energy today, but you saw it last year. I think you'll be fine with the packet. We'll do that on Monday, and PES on Monday. It sounds awful. It's really not bad. I promise you'll be good at it. We'll do several multiple choice questions together, and we'll do a lot of practice for your quiz. And I'm happy to alter the date for you because of Halloween. I didn't think about that. And so we'll quiz at the end of the week. But if you're not going to be here Friday, you take it before you go because you're ready for it on Wednesday or Thursday. You work that out with me separately. Write these up. Give it a shot. And we're still filming, so be careful.
Say that. Yeah, that's what I was. You always say that. No, I actually do know this.
I like to dump a bunch of my stuff out first.
Which already contains an electron, so then
Chase,
which in
that?
turn
Chase is like 5, 6.
it has
I'm giving it to the E, check your eye on E, so it's weird. Your eye to E was.
Plus it'll be, no, the nuclear charge, nothing changes in the nuclear charge.
How do you say centaur? How do you say centaur in the present progression? Centaur in the present progression.
It's just centando, it's not cientando.
That's like saying 100. That's like saying 108. No one's 86 feet.
You're saying the effects of the nuclear.
It's like saying I'm 108.
I remember something.
Cantando. I'm 108.
Alrighty, let's see how we did. I feel better. Explain why the electron affinity of nitrogen is less than that of carbon. Go ahead, Amelia.
Because an electron was added to the 2px shell, which already has an electron, so they repel each other.
And then just make sure you explain what electron affinity, so the ability to attract and hold that electron would be less. You got it. Down, this one's very easy. The second one's an honors level. Explain why the electron affinity of nitrogen is greater than that of antimony. Go ahead.
Antimony?
Antimony.
It's more of their atomic radius, which increases the electron shielding and electron-electron repulsion.
No electron repulsion. I wouldn't go there.
No, just the electron shielding.
Yeah, but also answer the question that's asked. Why is nitrogen's electron affinity greater? So nitrogen would be attracting and holding the electron to the second shell, closer to the nucleus, with less electron shielding, compared to antimony, which would attract it to which shell? The fifth period. You got it. All right, the last thing I want to mention very quickly, electron affinity, again, is the energy associated with the atom's ability to attract and hold an electron. Electronegativity is the tendency of a bonded atom to attract bonding electrons to itself. So, for example, if you have hydrogen fluoride, you're right, I know what you're doing. You're looking at the atom's ability to attract bonding electrons to itself. Fluorine is more electronegative than hydrogen, and those bonding electrons are pulled more toward fluorine than hydrogen. So electronegativity is the ability of a bonded atom to draw bonding electrons to itself. This trend is the same as that you have for electron affinity. So just to finish off, our little table here. We haven't done ionization yet, but electronegativity, like electron affinity, increases across a period and decreases down a group for the same reasons. Next time we're going to get into ionization energy. There'll be some new pieces to the puzzle, some review pieces, and we'll also get into PES, and they really do go together. I usually do them separately. I usually do all the trends together, but we reviewed in the beginning and had some stuff to finish up. So I think it'll work out fine. Please, for next time, you want a solid handle on what we've discussed. I'm going to give you the packet on periodic trends. Definitely worth your time. Get a good grip on this now. As we pushed back that quiz, a lot of you are not going to do any chemistry this weekend. Well, you could have a little mini quiz on Monday, so make sure that you are comfortable with everything we have discussed thus far.